Imagine a mystery unsolved for a century, a riddle about the very fabric of our universe. For decades, the Poincaré conjecture taunted mathematicians. If every loop on a three-dimensional sphere can be shrunk to a point, does that property define the sphere itself? Generations of brilliant thinkers chipped away, deploying ever more elaborate tools, but the heart of the problem remained unsolved. The problem gains a mythical stature in mathematical circles, having defeated countless mathematicians over a century. Prizes amounting to over $1 million are announced for anyone who can solve the problem. Then, in 2002, a slender set of papers appeared online, authored by a reclusive figure few had heard of, Grigori Perelman. In terse prose, he announced a solution that had baffled experts since Henri Poincaré sketched the conjecture in 1904. No fanfare, no conferences, just proof. The proof itself is said to be so complex that very few mathematicians can even follow and verify it. The announcement leaves the mathematical community in shock and awe. It takes fellow mathematicians a few years to become satisfied that the proof is indeed correct. Drama rippled through the community. Expositors raced to fill in gaps, and a war of words started. Some defended the need to clarify Perelman's concise arguments, while others tried to steal the credit. When the International Mathematical Union finally recognised Perelman, it offered him the Fields Medal in 2006, maths' highest honour. But, and it is a big but, for the first time in the history of the prize, someone declines the prize. "I don't want to be on display like an animal in a zoo," Perelman said, and retreated. 4 years later, the Clay Mathematics Institute offers Perelman the $1 million Millennium Prize. Again, he refused, saying, "I have all I want." This is the story of life and work of an enigma, the man who mapped the shape of space and chose to vanish from its stage. In June 1966, nestled among the austere grey apartment blocks of Leningrad, Yakov and Lyubov Perelman welcomed their only child, Grigori. The city was alive with the clang of tram bells and the snatches of song drifting from communal courtyards. While other children jockeyed over toy soldiers or chess pieces, Grigori was known to line up pebbles on the windowsill and mutter sequences of numbers under his breath. By the time he was 6, he'd taught himself to recite prime numbers up to 3 digits, astonishing neighbours who discovered him late at night scribbling long addition tables on scraps of newspaper. His mother recalls that he often skipped supper, lost in a whirl of arithmetic, until his father fetched him by the collar and insisted on a plate of food. At age 10, Perelman joined the legendary Sergei Rukshin's after-school math circle. In a cramped classroom where chalk dust floated like early snow, children furiously solved problems on the blackboard, a spirited forum of proof and counterproof. Here, Grigori encountered his first real puzzle, a deceptively simple question on polygon intersection that took weeks for even the oldest students to crack. He solved it by lunchtime. By 14, rank prize competitions and regional contests were mere warm-ups. In 1982, at 16, he travelled to Budapest for the International Mathematical Olympiad and returned with a perfect score, an honour shared by a handful of competitors in the contest's decades-long history. Invitations to elite Soviet schools poured in. He enrolled at Leningrad Secondary School, 239, famed for nurturing math prodigies, forging friendships with peers who would later become collaborators on the world stage. His reputation preceded him when, instead of sitting for entrance exams, he received direct admission to the renowned Matmik faculty of Leningrad State University. Their rigorous lectures on topology and differential geometry fed his relentless appetite for abstraction. By the late 1980s, Perelman began publishing papers on convex surfaces and saddle shapes, quietly signalling the arrival of a mind destined for deeper breakthroughs. As Grigori Perelman moved from classroom puzzles to original research in the late 1980s, he turned his attention to the geometry of shapes, both familiar and exotic. In his undergraduate studies, Perelman dealt with issues in the field of convex geometry. Imagine any shape, say, a rubber band stretched around a cluster of pins on a board. The rubber band encloses a convex shape if every line segment joining 2 points on the rubber band stays entirely within it. His first published article studied the combinatorial structures arising from intersections of these convex polyhedra. Perelman studied how these shapes intersect and fit together. In one paper, he asked, if you push 2 convex volumes together, how many faces can their overlap have? He answered by counting edges and faces, much like counting regions on a soccer ball. His results tightened earlier estimates, showing that intersections can be surprisingly simple even when the original shapes seem complex. Surfaces of negative curvature were the subject of Perelman's graduate studies. Think of a saddle. It curves up one way and down the other. That's negative curvature. A hypersurface is an object like a curved sheet in higher dimensions. Perelman examined how these sheets bend and twist. He proved that under certain bending rules, negatively curved hypersurfaces behave predictably. No weird folds or creases can suddenly pop up. If you hold a thin, saddle-shaped sheet and gently stretch it, Perelman showed you can always smooth it without tearing. Perelman's first works to have a major impact on the mathematical literature were in the field of Alexandrov spaces, the concept of which dates back to the 1950s. Imagine hiking across a landscape of rocks and hills, where the ground can suddenly jut out or dip without warning. In comparison geometry, we learn how walking in such a place differs from moving on a perfectly smooth surface like a flat plane or a gentle sphere. Alexandrov spaces extend this concept to shapes that may have sharp corners or uneven curvature, yet still let us measure distances and angles reliably, just as if the space was smooth. Perelman proved that even when the curvature jumps abruptly, these bumpy spaces hold together, so you can draw triangles, compare side lengths, and trust that the space won't tear or fold unexpectedly. For his work on Alexandrov spaces, Perelman was recognised with an invited lecture at the 1994 International Congress of Mathematicians. In 1972, mathematicians Jeff Cheeger and Detlef Gromol established an important conjecture called the Soul theorem. This was Perelman's first major breakthrough. Imagine a perfectly smooth hill that slopes gently in all directions. The Soul conjecture asks, can you compress that entire hill continuously without tearing or cutting down onto a simpler, lower-dimensional shape at its heart? Perelman proved that for any complete space with non-negative curvature, there is a unique, most compact soul where the entire shape deformation retracts. Rather than studying an infinitely large curving surface, mathematicians can focus on this finite core subset, the soul, that captures all the essential geometry. Perelman's 4-page proof demonstrated that no matter how vast or gently rounded the space, it always collapses neatly onto its soul, like peeling an onion down to the final layer. This elegant result laid a foundation for controlling the behaviour of shapes in higher dimensions, streamlining decades of complex theory into a simple, powerful principle. A story now turns to a problem that had haunted mathematicians for nearly a century, the Poincaré conjecture. This was the Everest of mathematical challenges. In 1904, Henri Poincaré observed that on a perfect 3-dimensional sphere, every closed loop, no matter how tangled, can shrink to a single point. He conjectured the converse. If a space shares this looping property, it must itself be a sphere. Early 20th century trials by James Alexander and Oswald Veblen provided partial progress, but a full proof eluded them. Through the 1960s and 70s, pioneers such as Stephen Smale and William Thurston revolutionised topology, introducing surgery techniques and the concept of geometrization. But the three-dimensional case remains stubbornly out of reach, trapped by complex knots and unpredictable singularities. In 1982, Richard Hamilton introduced a mathematical technique called Ricci flow. Under Ricci flow, a shape's irregularities can be smoothed out over time, just as a hot metal plate evens out temperature. Hamilton's plan was to use this process to reveal a manifold's true topological nature, if only one could navigate the singular pinch points where curvature spikes uncontrollably. By the year 2000, the Clay Mathematics Institute declared the Poincaré conjecture a Millennium Prize problem, offering $1 million to anyone who could solve it. Grigori Perelman's key insight was to treat Hamilton's Ricci flow not as a one-way street heading towards singularity, but as a process he could guide, control, and even repair. He began by proving that under Ricci flow, no region of the manifold could simply vanish. Like a sculptor watching every chip of marble hold its volume, Perelman showed that as curvature evolved, each patch of space retained enough heft to track its journey. This non-collapsing property meant the flow could be followed continuously, without losing pieces of the geometric puzzle. Next, he turned to the nature of the trouble spots themselves. Observing countless scenarios where curvature spiked, Perelman classified these singularities into two familiar shapes: a thin, cylindrical neck or a rounded, dome-like cap. By mapping every possible high curvature region to one of these canonical models, he transformed an unpredictable threat into a predictable, manageable list. Armed with this classification, Perelman devised what he called surgery. Whenever the flow created a neck pinch, he would slice through the problematic tube, remove the distorted region, and seal the gap with a standard cap. With each finite cut and patch operation, the manifold's topology simplified, steadily revealing its true spherical nature. His 3 concise papers, published online in 2002 and 2003, laid out these steps in tight, confident prose. Through prudent volume preservation, singularity classification, and surgical intervention, Perelman completed Hamilton's vision. Perelman's manuscripts were famously terse. No long introductions or footnotes, just rigorous arguments laid out with quiet confidence. By 2004, experts worldwide had verified each step. The conclusion was unambiguous. The Poincaré conjecture was solved. When word of Perelman's proof rippled through the mathematical world, it ignited a fever of celebration and controversy. In 2006, the International Mathematical Union announced that Grigori Perelman would receive the Fields Medal, widely regarded as the highest honour in mathematics. For most recipients, the announcement is the culmination of years of conferences, ceremonies, and photo ops. But Perelman did not travel to Madrid to step onto the podium. Instead, he issued a brief statement. "I don't want to be on display like an animal in a zoo." He declined the medal, the first time in the history of the prize, sending shockwaves through the community. In 2010, the drama resurfaced when the Clay Mathematics Institute offered Perelman the $1 million Millennium Prize for solving one of its 7 greatest unanswered questions. Once again, Perelman refused. When asked why, he replied simply, "I have all I want." This double refusal fueled endless speculation. Some colleagues praised his purity, that a desire for truth eclipsed any hunger for accolades. Others saw a critique of mathematical culture, where competition and credit sometimes overshadow collaboration and honesty. Behind closed doors, tensions flared into outright disputes. Two groups raced to claim and publicise detailed versions of Perelman's proof. In Hong Kong, Huaidong Gao and Xiping Zhu, students of Fields medalist Xing Tung Yao, released a monograph asserting they had provided the first complete exposition. Shortly after, John Morgan and Gang Tian published their own account, suggesting they had filled in the crucial gaps. In a rare interview, Perelman lamented the erosion of ethical standards in mathematics, hinting at certain authors of overstating their role and diluting his ownership of the proof. His refusal of prizes was not a rejection of honour per se, but of the performative rituals around it. To Perelman, the Fields Medal and Millennium Prize were symbols that risked turning a proof into a spectacle. He believed the work itself, etched in the silent language of mathematics, was its own reward. In declining these awards, he reframed the conversation about recognition in science. At the height of his newfound fame among mathematicians, Perelman was offered positions at Stanford and Princeton. He turned these down as well. When asked why, his simple response was, "They asked me for a CV." Returning to Russia, Perelman moved into his mother Lyubov's modest apartment to take care of her in her old age. His daily routine is said to involve long walks along Leningrad's outskirts at dawn, small wicker basket in hand, eyes fixed on the forest floor in search of chanterelles and boliters. Perelman's appearance mirrored his lifestyle. His fingernails grew long. Some say he did not trim them, so he could feel the texture of chalk dust more keenly when writing proofs on slate blackboards. His clothes were unremarkable, plain trousers and a worn sweater, as if to blend into the background. He rarely received guests. The building's elevator sat unused by his door because he refused to share it with strangers. When journalists or fellow mathematicians sought him out, he offered the same polite rebuff, "I'm picking mushrooms." It was a phrase both literal and metaphorical, an apology delivered with quiet dignity, a world away from conference rooms and lecture halls. Those who caught a glimpse of Perelman during work reported an unusual sound, a low hum, almost a half moan, rising and falling as he immersed himself in a stubborn calculation. It was not discomfort, but concentration made audible, a private soundtrack to a mind wholly absorbed. He avoided interviews and refused invitations to seminars. Yet, behind the reclusion lay a fierce integrity. Perelman saw mathematics as a pure dialogue between thinker and theorem, unsullied by publicity or ceremony. Awards, he believed, risked turning proof into performance, shifting focus from discovery to display. This conviction drove him to eschew honours and maintain distance from the academic establishment. In the years since, Perelman has remained off the public radar. Reports place him in a quiet suburb of St. Petersburg, living with his mother, tending to her needs, and pursuing mathematics on his own terms. He shares ideas through brief notes passed to trusted colleagues, but he declines to publish or present. Grigori Perelman's life is a testament to singular dedication. A scholar who chose solitude over acclaim, principle over pomp. In the silent corridors of his modest apartment, he continues to follow the lines of proof wherever they lead, untethered by the world's applause, guided only by the logic of discovery. In a world chasing acclaim, he reminds us that the truest discoveries dwell in silent proof where the joy of truth outweighs every applause.